Hello, let me first thank everyone who listens to this and apologize to everyone for not being able to actually come to the meeting. I've had some health problems, including one that prevents me from flying, at least for the immediate future. So I'm sort of stuck here in Ann Arbor. So what I want to talk about today has a somewhat vague title, Ultrafilters Containing Intersections. Let me begin with a couple of slides of background just to make sure that we're all on the same page. For most of this talk, all except maybe the last couple of slides, the ultrafilters that I talk about will all be on countable sets. And as a result, I may as well think of them as being on the set omega of natural numbers. If I need them on some other set, well, I just use a bijection between that other set and omega. So I'll give some definitions referring to omega, but they work equally well for other countably infinite sets. I'm also likely to assume ultrafilters that I talk about are non-principal. My general policy here is that if I say something that presumes the ultrafilters are non-principal, you should assume they are. If I say something that presumes that you allow principal ultrafilters, you should assume that I allow them, and you should oscillate back and forth as needed so that what I say is actually true. I need two constructions of ultrafilters in this talk. One is simply the image of an ultrafilter under a function. So I have an ultrafilter U on omega and a function from omega to omega. The image of the ultrafilter, f of u, is defined to be the ultrafilter consisting of those sets X whose inverse image under F is in U. This is a completely standard definition of pushing forward an ultrafilter along a map. It would work equally well if U was an ultrafilter on some other set and F mapped that other set into yet somewhere else. F of U would be on that yet somewhere else set. The second construction that I'm going to need is a somewhat more complicated one that takes some ultrafilters on omega and produces an ultrafilter on omega squared. And this definition is not the easiest thing in the world to read, so I'm going to wave my hands at it instead of saying it normally. Think of omega squared as the plane, or as the integer lattice in a quarter of the plane, with omega along the base and omega vertically. Think of the ultrafilter U as being an ultrafilter on that base, on that copy of omega, and think of V sub I as being an ultrafilter on the ith column, the column above the number I of the base. And then this ultrafilter that I've written as the summation of the V sub I with respect to U is the ultrafilter consisting of those sets in the plane, such that for almost all points in the base, almost all with respect to U, the set in the plane contains almost all points in that vertical column. So it's for almost all X, for almost all I, for almost all J, IJ is in that set. The other piece of background that I'm going to need is not constructions, but properties of some ultrafilters. They're fairly commonly used ones. They've probably been used in other talks at Ultramath, but since I'm not there, I can't just refer to other people's talks. So an ultrafilter is selective if whenever you have a function on omega, there is a set in the ultrafilter on which that function is one-to-one or constant. And the definition of a p-point is almost the same. The only difference is that instead of one-to-one, it says finite to one. So being a p-point is a weaker property than being selective. the information that we need about these is, well, first of all, whether these kinds of ultrafilters exist is independent of the axioms of set theory. There are models of ZFC where there are no selectives and not even p-points. On the other hand, in models that satisfy the continuum hypothesis, there are a great many selective ultrafilters, a great many p-points that are not selective, and so on. But in general, in ZFC alone, all one can say is, well, there are definitely ultrafilters that are not p-points, but anything beyond that, whether they are p-points or selective and so on, independent. With that background, I can now talk about the questions that I want to address. As the title says, ultrafilters that contain intersections. So when does an ultrafilter contain the intersection of some of its members, some of the sets in the ultrafilter? Well, if you're intersecting finitely many sets, then of course, the answer is always, because it's part of the definition of a filter that it's closed under finite intersections. So that's not very interesting. On the other hand, if you intersect countably many sets in the ultrafilter, then in general, you will not get a set in the ultrafilter. In fact, you're likely to get an empty set. The word never on the slide refers back to the convention on the first page that I will be dealing with ultrafilters on omega and non-principal ones, because principal ultrafilters are closed under arbitrary intersections and therefore not interesting in this talk. And if ultrafilters were not on omega, but on some measurable cardinal, then they could indeed be closed under countable intersections. But on omega, non-principal ultrafilters are never closed under countable intersections. I put an extra clause here on the slide. Of course, the ultrafilter may contain the intersection of some countably many of its elements. That's easy enough to arrange. Pick one infinite, co-infinite set in the ultrafilter and take its supersets, or take countably many of them. If you let me choose which countably many sets to intersect, then I can arrange for the intersection to be in the ultrafilter, but that's not very interesting. The question I want to look at is this. Written here, given many sets in U, are there many among them whose intersection is in U? And I hope you notice that I wrote one many in capital letters, the other in lowercase letters, to suggest that the first many is more than the second many. That is to say, the problems that I want to look at are of the form, given a very large number of sets in an ultrafilter U, will there necessarily be a moderately large subfamily whose intersection is still in U? Not necessarily as big as the original very large family, but still moderately large. So that's the kind of question that I want to look at. A variant, a minor variant of that question, given many sets, again, capital many, very large number of sets, but not necessarily in U, in the power set of omega, just some subsets of omega. So some might be in U, some might not be in U. Can I find many, lowercase many, so a reasonably large number of them, such that a single set U, a single set A in U is either included or disjoint from each of them? The point is that if I want a set in U, among the sets that I choose, these highlighted many among them, the ones in U should then include A, and the ones not in U, well, the complements are in U, so those complements should include A, meaning that A should be disjoint from them. In this situation, I will often say that A decides those sets, the idea being that A is included in some of them, and therefore they have to be in the ultrafilter, and A is disjoint from others, and therefore they have to not be in the ultrafilter. So A decides whether A decides for each of these sets whether it is or is not in the ultrafilter. So that's what I mean by deciding a bunch of subsets of omega. This sort of question occurs in two contexts. Well, actually in more than two contexts, but I'll spend most of this talk on just two contexts. One is concerned with the two-key ordering of ultrafilters. So I need to introduce that. It may, again, have already been mentioned in other talks, but I don't think I can count on that. So here is the two-key ordering. It's ordering on, no, an ordering of directed sets. So first of all, a directed set is a partially ordered set in which every finite subset has an upper bound. Of course, instead of finite subsets, it's enough to say it for two element subsets and the empty set. So every two elements have an upper bound, not necessarily a least upper bound, just an upper bound. And there's at least one element, an upper bound for the empty set. In a partially ordered set, I call a subset cofinal if it gets above all the elements of the whole partially ordered set. So every element of the partially ordered set has something above it in this cofinal set X. And a subset is unbounded if no single element of the partially ordered set is above all the elements of X. So given any element of P, at least one element of X is not underneath P. With those definitions, I can now say what the two-key ordering is. It's an ordering of the class of all directed sets, so directed partially ordered sets. And the definition is that one such directed set P is two-key above another Q if there's a function from P to Q, from the bigger to the smaller in the ordering, such that cofinal subsets of P get sent to cofinal subsets of Q. So a function P to Q that preserves the property of being cofinal. That turns out to be equivalent to the existence of a function in the other direction, Q to P, smaller to larger, that preserves the property of being unbounded. Unbounded subsets of Q have images that are unbounded in P. I will say a little bit more later about the reason for the equivalence. Right now, I'm just giving it as two versions of the definition. By the way, when it comes to proving anything, I've decided that in order to finish this talk in anywhere near the appropriate time, I'm going to omit the proofs from the talk. I do have some slides at the end, after the official ending of the talk, that contain those proofs, and I'll be emailing those slides to the conference organizers so that I hope everybody will be able to access them if they want to see at least sketches of the proofs. I want to say something about the motivation for this two-key ordering, and there are actually two motivations. The original one, due to two-key, is from topology. You notice that there are lots of statements that one can make about sequences in metric spaces, functions from the natural numbers to X, that don't work in more general topological spaces. For example, a point in the closure of a set in a metric space is a limit of a sequence approaching that point, with all terms of the sequence being in that set. That's not true in general topological spaces. But it can be made true if you generalize. Instead of looking just at sequences indexed by the natural numbers, you index with more general directed sets, allow arbitrary directed sets, and then the analog of this characterization of closure becomes true in that framework. These generalizations are called nets. A net in a space is just a function into that space from a directed set. In order to handle many of the topological things normally done with sequences, one needs a suitable notion of subnet. And there are variations in the literature as to what is the suitable notion of subnet. One such notion, the one I like, is to simply compose a net. So if I have a net, a subnet is the composite of that with a function from some other directed set. So it will be a new net with domain P instead of Q. And F needs to do exactly what is asked in the definition of Tukey ordering, send cofinal sets to cofinal sets. And that works, for example, with theorems like if a sequence converges, so does every subsequence in a metric space. Now, if a net converges, so does every subnet. Slightly more complicated. If a net has the property that every subnet has a further subnet converging to a particular point, then the original net converged to that point. Things like that we know for sequences work for nets and subnets in this sense. So this, I think, was essentially the original motivation for Tukey to define this topic. There's a second motivation from set theory. Peter Wojtasch noticed that this has a lot to do with cardinal characteristics of the continuum. Specifically, if I have a function f sending cofinal sets to cofinal sets, there will automatically exist, as I claimed a couple slides ago, a function the other way. A couple slides ago, I said, preserving unboundedness. Now I'm going to say something more. Well, something different. Namely, that if you take a point in P and a point in Q, then this new function maps little q below little p implies that the original function maps little p above q. So an inequality here holding in P implies an inequality here holding in Q, and the two inequalities are related to each other by these two functions f and g. It turns out to be an easy exercise to check that the g, any g that does this, will in fact send unbounded sets to unbounded sets. And there's a converse to this. If I have a g that sends unbounded sets to unbounded sets, then there is an f, a function in the other direction, satisfying this implication. And again, it's easy to check that such an f will send cofinal sets to cofinal sets. So this is where one gets the equivalence of the two definitions of the Tukey ordering. What Peter Wojtasch noticed is that the same relationship between two functions occurs in more general contexts, not only maps between directed partially ordered sets, but more generally maps between all kinds of sets with various relations among them, replacing the ordering relations. In fact, he showed that a great many proofs in the theory of cardinal characteristics of the continuum are basically constructions of such pairs of maps, F and G, related by that implication at the top of the slide. So he systematized a lot of this. He called such pairs of functions generalized Galois-Tukey connections from Q to P. Tukey because of the connection with the Tukey ordering. Galois because it actually also has a connection with the Galois correspondence in algebra between Galois groups of fields and intermediate extensions of fields. I called them morphisms from P to Q. The P to Q was motivated by the fact that the implication here goes from something holding in P to something holding in Q. And changing the name to morphism was, I wanted a new name so that we're not arguing about which way a generalized Galois-Tukey connection goes. And also, I wanted a shorter name. So, and I was thinking in terms of categories, so I just called them morphisms. But they're really the same thing. Okay, now I want to get back to the Tukey ordering and eventually connect with ultrafilters. Oops. If you take a directed set of cardinality kappa, it is always Tukey below this directed set. This is the set of finite subsets of kappa ordered by inclusion. Notice that is directed given any finitely many finite sets. There's an upper bound, the union, still a finite set. It's directed, and let's see, I want to show that a directed set, if it has cardinality kappa, is Tukey below this. So I need to take, I should take the first definition of the Tukey ordering and say there should be a map from these finite subsets of kappa to this arbitrary directed set of cardinality kappa that respects cofinality, sends cofinal to cofinal. And this is easy to do. You enumerate arbitrarily the directed set you're aiming for in a sequence of length kappa. You send each singleton in kappa to the less than omega to the corresponding element in your partially ordered set. And if you have a finite subset, well, that gives you finitely many elements in your directed set, and you take any upper bound of them. That's the image. And again, it's easy to check that that is cofinal. In fact, it's easy to check a bit more, which, yes, I did put it on the slide. It's not really essential that the target set itself have cardinality kappa if it has a cofinal subset of cardinality at most kappa. That's good enough. Okay. By essentially the same argument, you just map to that cofinal subset. If you fix kappa and look at directed sets of cardinality at most kappa, then among such sets, this is the top one in the Tukey ordering. So it is called Tukey top, and anything equivalent to it, equivalent in the sense of being Tukey ordered with it in both directions, is also called Tukey top. So Tukey top just means at the top of the Tukey ordering for its cardinality. Oh, and there's a comment that I guess I will need later. A subset of this particular directed set is unbounded if and only if it's an infinite set. Okay. So now I'm going to apply this to ultrafilters on omega. Of course, an ultrafilter on omega has cardinality of the continuum, and it's a directed set when ordered by reverse inclusion. So bigger in the ordering means smaller as a set. It's also directed in the forward inclusion, but that's kind of silly because of just omega itself is the largest element of the ultrafilter. So when I talk about ultrafilters as directed sets, I mean directed with smaller sets being bigger in the directed set. With this terminology, a cofinal subset is a subset of the ultrafilter that eventually gets inside every set of the ultrafilter. That's just a base for the ultrafilter. And I put in here the statement that the non-principal ultrafilter never has a countable base. That is quite easy to check. I don't think I'll actually need it in the talk because it's used in one of the proofs that has been postponed past the end of the talk. An unbounded set, in the sense of this directed partial order, is simply a subset of the ultrafilter whose intersection is not in the ultrafilter. So you can see we're at least making some contact with this original question of ultrafilters containing intersections of some of their sets. It's essentially saying that some such intersections should be bounded. There was a theorem of Isbell, one of the first theorems about Tukey, or maybe the first theorem about the Tukey ordering of ultrafilters. There exist Tukey top ultrafilters on omega. This label on this slide is a little bit dishonest. I'm proving Isbell's theorem, assuming a fact that is proved on the slide past the end of the talk, namely that there are independent families of continuum many subsets of omega. So F is a family of continuum many subsets of omega, such that if you take any finitely many sets in F and any finitely many other sets in F, the intersection of the first finitely many and the complements of the second finitely many is an infinite subset of omega. So essentially, knowing that a point in omega is in certain elements of F and out of certain other elements of F doesn't tell you very much, because there's still infinitely many points that do that. It is a theorem originally due to Fichtenholz and Kantorowicz, but proved more nicely and generalized by Hausdorff that such a family F exists. Furthermore, the proof, both of the proofs, Fichtenholz and Kantorowicz, as well as Hausdorff's proof, provide an analytic example. Analytic here refers to, well, F is a subfamily of the power set of the natural numbers. It therefore can be viewed as a set of reals, identifying subsets of omega with reals. With the usual topology on the reals, you have a notion of Borel set, and continuous images of Borel sets are analytic sets. Such an F, the examples are analytic. That is all that's going to be needed. In fact, I think they're actually Borel and fairly low-level Borel if you're careful about it, but analytic will be good enough. So here's Isbell's theorem. Take the cardinal of the continuum, which I call German C here, and biject it to this independent family. Take all the intersections of infinitely many sets from F. What I want is an ultrafilter that contains all the sets in F, but the complements of all the sets in B. So it contains every set from F, and therefore every finite intersection of sets from F, but no infinite intersection of sets from F. And the independence of the family F guarantees that these things that I want in my ultrafilter do generate a filter, and therefore I can extend it to an ultrafilter. And this ultrafilter works. One-line proof, I guess. I'm going to define the G, the function that preserves unboundedness, from let's see, yeah, this is the right one. The one that preserves unboundedness from the top to U. That puts U greater than or equal to the Tukey top, and therefore U itself is Tukey top. And the way it works is just, well, given a finite subset of C, you apply B to those finitely many elements. That gives you finitely many elements in F, and intersect them. That gives you a set in U. Since unbounded subsets to unbounded subsets, that needs a little checking, but it's essentially just observing that all the infinite intersections of sets from F have been removed when we formed U. A side comment, the same construction of an ultrafilter from an independent family is also the standard proof that some ultrafilters, like this U here, cannot be generated by fewer than continuum many sets. It's also the standard proof that the number of ultrafilters on omega is 2 to the cardinality of the continuum. So this is a familiar construction, even apart from its use for the Tukey ordering. So the next question is, are there ultrafilters on omega that are not Tukey top? Isbell says, here's one that is. Are there any that are not? That's an open problem, which is part of why I got interested in this. Even though I'm interested, it's still open. The answer is consistently yes. There are models of ZFC in which there are non-Tukey top ultrafilters, but no one has been able to prove that in ZFC without some special hypotheses. First theorem, I hope I'm attributing this correctly, due to Dilip Raghavan and Stevo Todorcevic, is that P points are never Tukey top. So if you're in a model of set theory where P points exist, then the answer to the open problem is yes, there are non-Tukey top ultrafilters. But thanks to Sherach, we do have examples of models in which there are no p-points. The proof proceeds via an intermediate step, and I'm not sure how much I should do with these intermediate steps. Well, I guess I will finish this. Every p-point has the property of being basic, which means that if a sequence of countable ordinary sequence, not a net, a sequence of elements of U converges as reals in the usual topology of this version of the reals, then it has a bounded subsequence, bounded in the sense of the Tukey ordering. Its intersection, the intersection of that subsequence is in the ultrafilter. So one proves that property of p-points. And then the second part of the argument is if an ultrafilter is basic, or even if it's basically generated, which means, pardon the terminology, it has a basic base closed under finite intersections. Not my terminology, I hasten to add. Then it is not Tukey up top. In fact, it's not even Tukey above Aleph 1 to the less than omega, let alone what Tukey top would require, continuum to the less than omega. So basic generation is the tool used here for getting things that are not Tukey top. Natasha Dobrinin, Dilip Raghavan, and I also had a construction of an ultrafilter that is Tukey top for a somewhat different reason. It is not basically generated, but still not Tukey top. I want to say something about the combinatorics involved in Tukey top ultrafilters. I also want to finish in finite time. We'll see how that goes. If I have a bunch of basically generated ultrafilters and I form this ultrafilter that I described at the beginning of the talk on omega squared, this will also be basically generated. It's never a p-point. So this gets you, if you have some p-points, you get some non-Tukey top ultrafilters because they're basically generated that are not p-points. Just let U and VI be a bunch of p-points and take the sum. Another corollary of what was on the last page is that if an ultrafilter, sorry, that's not a corollary. This is restating the definition of Tukey top in negated form. An ultrafilter is not Tukey top, so the kind of thing that we don't know whether it exists. If whenever you have continuum many sets in U, infinitely many of those continuum many have an intersection in U. A couple of equivalent formulations, one equivalent formulation. Given continuum many subsets of omega, there should be one set in U that decides not all of them, but infinitely many of them. Corollary of that is what I was about to say earlier, that if an ultrafilter is generated by fewer than continuum sets, then it is not Tukey top. Non-Tukey top ultrafilters, I think I will, this slide is just repetition. The non-Tukey top ultrafilters contain all p-points and anything generated by less than C sets. And the collection of basically generated ultrafilters also contains p-points and is closed under summation. So this is sort of a summary of where we've been able to get our hands on some non-Tukey top ultrafilters. So now I want to switch gears and talk about a different property related to intersections still being in an ultrafilter. This has to do with forcing. Suppose I have an ultrafilter, and now I extend the universe by forcing to get a V of G. If you don't like extending the universe, pretend that my V is a countable transitive model, that U is in that countable transitive model, and then extend by forcing. However you like to do forcing, the story is the same here. Preserved means not that it's still an ultrafilter. The only way that can happen is you don't add reals. Then, of course, yeah, the notion of ultrafilter doesn't change. The crucial thing is, does it generate an ultrafilter? Is it a base for an ultrafilter in the extension? That's what I call preserved. Another way to say it is every subset of omega in the extension is decided by a set in U. It's either superset or disjoint from a set in U. Another way to say the same thing again is that there's no set in V of G that splits all the sets in U. Non-preserved is killed. Now we have to clear away some underbrush, some things that are not really important but need to be said to get this problem focused in the right way. So first of all, I mentioned already, if a forcing doesn't add reals, there's nothing to say here. All ultrafilters are automatically preserved. We're interested only in forcing extensions that do add reals. Some kinds of new reals simply split all infinite ground model sets and thereby kill all ultrafilters. Among these are Cohen reals and random reals. There are other kinds of reals like Matthias Reels. A Matthias reel does not itself split all ground model reels. It does get into or out of each one eventually, but from a Matthias reel, you can easily define other reels that split all the ground model reels. And the same is true not only for Matthias reels, but for Lever reels, and in fact, any forcing that adds a dominating reel. If you add a dominating reel, you have killed all the ultrafilters. Well, okay. Maybe you always kill all ultrafilters. Wouldn't that take care of the problem? It would, but that's not true. Can you preserve an ultrafilter while adding new reels? The answer is consistently yes. Selective ultrafilters are preserved when a Sachs reel is added. And in fact, even if you add an omega-2 sequence of Sachs reels with countable supports, this is an old theorem of Jim Baumgartner and Richard Lever. P-points are preserved when you add Sachs reels, also when you add Miller reels. The result for Miller reels is in, I think, Miller's original paper introducing Miller forcing, that P-points are preserved when the Sachs reel is added. I may have been the first person to say that, but the proof is certainly in Miller's paper. It's just a matter of look at the proof and see what it gives you, and it gives you that. And you can again iterate those. It's a general fact due to Schelach that proper forcing iterations that preserve P-points at every step preserve P-points at limit stages as well. The connection between P-points and preservation is an interesting one for the following reason. If a forcing adjoins a new reel that is not majorized by a ground model reel, then the only ultrafilters it could possibly preserve are P-points. Any preserved ultrafilter is a P-point. This applies, for example, to Miller forcing. On the other hand, if it doesn't do that, if every new reel is majorized by a ground model reel, and I have to assume that the forcing is a proper forcing, in the sense defined by Schelach, then if it preserves U and the V's, it also preserves the sum, which means in particular, it will preserve some things that are not P-points. In particular, Sachs forcing, which is proper and omega to the omega bounding, preserves not only P-points, that was on the previous slide, but some other ultrafilters as well, namely anything you can get from P-points by summation. I put in parentheses if it preserves anything, because of course we don't know that there are P-points. We don't know it in ZFC at least. All right, so maybe there's a forcing, Sachs maybe, that preserves all the ultrafilters. Well, no. If you add a reel, you kill some ultrafilters. The theorem is a forcing extension adds new reels. It kills some ultrafilter. This is where I got into this business to begin with. I had heard this theorem frequently and had never really worked through a proof of it. And at one point, some years ago, I decided I should really learn this proof. It's in the book of Bartoshinsky and Yuda. So, and it's not that long. It's like maybe 1 or 1.5 pages. So I read it and it's a, it works. And then I sort of tried to organize it a little so that I could have a better view of how it works and so on. And I noticed that the proof actually shows more. You can switch the quantifiers. It's not just given a forcing extension, there exists an ultrafilter. It's there exists an ultrafilter that works for every forcing extension that adds reels. Even more, there are lots of these ultrafilters. The formal statement is there's an analytic filter on omega such that all its ultrafilter extensions are killed whenever you add reels. The point of analytic ultrafilter is that such a thing is very, very far from being, the point of analytic filter is that it's very far from being ultra. So there will be many ultrafilter extensions. Very far can be formalized as a finite to one function such that the image of this filter consists of only the cofinite sets, which is about as far from ultra as you're likely to get. History. So what I said a moment ago is how I fumbled through this area. It turns out that a lot of this stuff was already known. The additions that I had where the proof gives more and yet more are in fact in a paper of Bartoszyński, Goldstern, Juda, and Schelach, whose title doesn't actually give the hint that this is about preserving ultrafilters, but okay, it's in there. One can do even better. A very specific filter. The proof in Bartoszyński Juda does give a way of constructing a specific filter like that, but David Hodonskios, Lado Guzman, and Michael Hushak have shown that you can simply take the filter of subsets of omega whose asymptotic density is 1, and all its ultrafilter extensions are killed whenever you add new reels. Okay, so some ultrafilters are going to get killed for sure. Other ultrafilters, what does it take for an ultrafilter to be preserved by some forcing? Here's a theorem of Arnie-Miller. Given an ultrafilter, the following are equivalent. The first is what I just asked, a forcing that adds new reels, but still preserves U. The second is, never mind arbitrary forcings, if any forcing can do that, Sachs forcing does it. This is, I guess, a special case of the general but very imprecise principle that Sachs forcing is the gentlest possible way to add a reel. And the third is where we connect to the subject of today's talk. Every perfect subset of the power set of omega has a perfect smaller subset, all of whose members are decided by a single set in U. I might add that, since I mentioned earlier about the title not giving you a hint about what it's about, the title of Arnie-Miller's paper is Ultrafilters with Property S. And you might think property S should be these equivalent properties here, but no, it's not. I don't have time to go into what it is, but the main result in the paper is, in fact, the property S is not equivalent to what's given here. A slight reformulation of 3. It starts the same way. Every perfect subset has a, instead of perfect, I now say uncountable subset, all of whose members are decided by a single A. The point is that the things decided by a single A are a closed set in the usual topology of the reals. So if such a set is uncountable, it automatically has a perfect subset by a theorem of, I guess, Cantor and Bendixson. Another corollary of this is when an ultrafilter has a base smaller than continuum, it's preserved by Sachs forcing. Another corollary, Isbell's Tukey top example, is not preserved by any forcing because essentially the Isbell construction hands you a perfect subset that does not have a lot of members decided, not even, doesn't have uncountably many, it doesn't even have infinitely many members decided by a single A. So here's a summary of information about preservable ultrafilters. Ultrafilters that can be preserved by some forcing that adds Reels, or more briefly, that can be preserved by Sachs forcing. This collection contains all P points, contains all ultrafilters generated by fewer than continuum many sets, and is closed under summation. This looks an awful lot like the summary slide that I had for the property of being not Tukey top. Let's compare. Combinatorial characterizations. Not Tukey top is every continuum many subsets of omega have infinitely many decided by a single set. Preservable is equivalent to every perfect family has an uncountable subfamily decided by a single set. So the second version has the stronger hypothesis. Starts with a perfect subfamily, which would, of course, then have cardinality C, rather than a completely arbitrary family of cardinality C. But the second also has a stronger conclusion, uncountable subfamily, rather than infinite subfamily. And yet, we have all these similarities. For instance, P points automatically do both of these. The Isbell example automatically does neither of these, and so forth. It seemed reasonable to me to try for a common strengthening. Let's mix the weaker hypothesis, continuum many subsets, with the stronger conclusion of uncountable subfamily. So the common strengthening is every family of continuum many subsets has an uncountable subfamily decided by one set. Can I get that common strengthening, for example, for P points? P points have both of the previous properties. Maybe they work with a common strengthening. Can an ultrafilter do this? Might all P points do it? CH implies no ultrafilter does this. On the other hand, Martin's axiom plus negation of CH implies that some ultrafilters do this. So this common strengthening is not totally ridiculous, but it needs stronger information than just existence of P points, which CH would give you. Okay, let's see, I'm almost out of time. That's all I want to say about forcing. I want to jump out of omega. I want to jump to a bigger context where we can have bigger intersections. I already mentioned, of course, that if you have a measurable cardinal, an ultrafilter can be closed under lots of infinite intersections. Here is what I think is a nice result of Galvin. It's actually a special case of a more general theorem that he proved. Like some of Galvin's results, he didn't publish it, but he allowed Baumgartner, Heinau, and Mate to publish it in a paper whose title again gives you no indication that it's about this particular topic. Suppose you have a measurable cardinal kappa and a normal kappa complete ultrafilter on it. Then if you take any kappa plus sets, so strictly more than kappa sets in the ultrafilter, among those you can find kappa whose intersection is in U. Okay, so I just wanted to throw this in to indicate that this business of very many sets in an ultrafilter include moderately many whose intersection is in U, comes up also out beyond omega, way beyond omega, at measurable cardinals. So I think that's actually a bit more than I had time for, so I'm going to stop there. Again, with the comment that there are more slides after this one. If anyone is interested in sketches of proofs, I will send the slides along with, assuming it all worked, the video of the talk. Okay, so I will stop there and see if I can stop recording.